Yes, yes.
We were like, maybe we should let it slide. No, we're not gonna insult their intelligence. It's obviously, we're sorry. We're under the gun.
Time moves differently.
Yeah.
So when you're in time, that's for sure. All right, so as a reminder, you guys have 15 minutes to present. I will give you warnings, the hand signal on 5, 2, and 1 minute. Additionally, once that's done, you have 15 minutes to answer any questions the judges have.
Cool. Will do.
Great.
Thank you.
All right, let me get the timer ready. As soon as you guys are good, I will start, and you are good to start.
Hello, esteemed judges. It is an absolute honor to be here amongst undeniable talent in these impressive facilities in the heart of Canadian innovation here. So my name is Clint. These are my teammates. This is Tom, Farhan, and Jimmy. And we are Team Barnacle. So it's a bit of a shame that this competition is putting themselves out during the summer because the Kitchener-Waterloo winter is a bit jarring for those of us who are from out of town. It makes you wonder, like, it must take an enormous amount of energy to heat this expansive facilities, all of these buildings across the Waterloo campus. And it turns out it takes even more energy to cool the buildings in the summer. In fact, according to the Independent Electricity System Operators, Ontario has drawn up to 27,000 megawatts of power on a summer day. A third of this power is going to air conditioning alone. And this is going to get even worse. The temperatures are predicted to rise anywhere from 2 to 8 degrees Celsius in the next few decades. So finding a way to passively cool buildings is important. There's a demand across Canada and worldwide. Thermochromic windows are a promising piece of this puzzle. They darken when hit with sunlight. This stops infrared radiation from coming into the building and warming it through that radiation. This is passive, uses no energy. And so our client, Lightshift, has hired us to help them automate the quality control process of the manufacturing of their thermochromic glass panels so they can scale quickly to meet demand. We were tasked with designing the building, robot prototype that could maneuver through their factory floor, identify defective glass panels, lift them up and take them to an area for recycling. All the while, this robot must handle all the glass panels really gently, and it must alert all bystanders with like visual or audio cues that the robot is in operation to avoid any accidents. So upon being presented with this problem, my team and I retreated to our design process, which we verbosely like to call our non-collaborative generative process. So you might assume that we had an open brainstorming discussion where we exchanged ideas back and forth with each other, but we did not. It's not what we did. In fact, some research has shown that brainstorming as a group can overrule the quietest voices in the group, and it can also stifle creativity before it's allowed to flourish. So instead, what we do is, upon being presented with the problem, we refrain from discussing all ideas immediately. Even when the problem was first given, we don't even whisper to each other. We try and keep ourselves completely unbiased from each other, not to influence the ideas. So we went to the design, our working room, and retreated for 15 minutes. Go back for a second. After 15 minutes, and then the solution generation, we then came together and amalgamated all the best ideas from every solution. So here's what we came up with. This team member's design had a low center of gravity, and they used an LED and a photoresistor pair to first shine the light, reflect it off the panel, and then sense it with the photoresistor. This pair is actually what we did end up going with in our final design. That was a great idea. This next team member came up with an idea to mount a dowel as an axle on a servo motor to place 2 forklifts that would rotate, scoop under the panel, lift it up. Forklifts work. Forklifts are everywhere. We didn't want to reinvent the wheel. This is a robust design. And we did end up going with this, except that in the end, we decided to build the dowel out of MDF. We had a big sheet of MDF. We're like, why not just build almost all the robot out of this one panel? So that's actually what we strove for, and we used almost consistently that one material the whole way. This next one continues this low center of gravity and maneuverability with short wheelbase. And this next one was done by one of the best, strongest artists on our team, and we're really proud of it. So I'll hand this off after just saying that our fundamentals of our design: small, low chassis, simple pivoting arms, caster wheels, photoresistor sensor, DC motors, and everything was made out of MDF with all of the fastening and bonding done with nuts and bolts where possible and not glue. So I'll pass it off to Tom to talk about the builds, problems, and the solutions we came up with.
So let's talk about problems that we faced. This competition lent itself to quite a few, both the mechanical side and on the coding side. But the biggest issue that we faced with the actual build was the lack of mounting hardware that was available to us. The application of our robot called for a robust, heavy-duty design that would withstand rigorous, repetitive tasks of testing and recycling the faulty glass. We didn't want to rely on the glue gun because it can be unreliable with the fastening. So by reinforcing any orthogonal mounts with MDF slots, we ensured a rugged design that would survive prolonged operation, reduce maintenance costs, and sorting downtime, and ensure reliability. To keep it expenses, for the axle of the forklift, we needed rotation, obviously. To implement this, we fashioned a cylindrical bore and shaft along the axis of the servo's rotation. We did this by increasing the width of the MDF by stacking layers and clamping them closed.
No, you're all right.
We're good.
You got it, buddy.
We then whittled the shaft into a cylinder. This ensured a consistent rotation without any deviation. To keep expenses to a minimum, we decided to construct the entirety of the robot out of single square foot of MDF. In manufacturing application, the design would be made from sheet steel, and having consistent build material not only keeps costs low, but reduces complications in sourcing from multiple distributors. I'm going to pass it to Ron, who's going to take us through the coding portion.
Thanks, Tom. Now I'm going to cover a portion of the software problems and some of the solutions we came up with. So photoresistors. We first needed to solve the problem of identifying a faulty window versus a non-faulty window. How we decided to do this was utilizing photoresistors. Now, the problem is, as we approach the mirror with our robot, we would lose the light around the area, the external features, the lighting in the room. So what we had to do was we had to put an LED beside it, because what we knew was the windows itself was a white gradient and a brown gradient. So what we could use was a visible spectrum of light, and realize that the brown absorbs more light. So as we approached it with an LED, we could see the gradient contrast, and that allowed us to basically dictate whether it was a faulty or a non-faulty window. Another thing we did was we optimized the scaling of it. So in software itself, we scaled down on values, so the range of detection was larger. And we also designed for a better resistor value to be in series with the photoresistor to encompass the larger voltage range. Now the IR remote control added some more complexities. We first tried to implement a library for the IR sensor, and what happened was we came into problems because nothing was working. It would spit out garbage values through the serial monitor. What we had to do was we had to dig through documentation and realize they were all outdated. So we rehashed the functions, and then once we got that working, it returned a 32-bit unsigned integer value to us. And what we had to do was basically, it's not very readable to the user, so we made enumerations for it, and for every button press, we just pulled it, wrote down the enumerations for that, and then wrote down the numbers for that, and then built out an enumeration, which we use in our switch statement to conditionally control the brains of the robot, essentially. Now there's another problem, the IR sensor, its noise really affects it, so what we had to do was place a bypass cap between the power rails, and also we had to account for blocking versus non-blocking, because we were using delay function, which basically stops and halts the processor, but we wanted to use millis, which was a more efficient implementation of reading that analog value. And now I will pass it on to Jimmy as he finishes off the software implementation.
Right, thanks, Ron. So if you look at the robot, you'll see that there's 4 wheels. 2 of them are casters, and 2 of them are wheels attached to motors. And these motors are attached to an H bridge. If you've ever used an H bridge, you know that there's 4 inputs, which means for us that there's a lot of housekeeping, a lot of pins that have to be set in very predictable ways, but it's a lot of code. So what we did was we created a class that could govern the motors, and we can instantiate each motor as an object that we can easily set the PWM and a direction. And this allowed for easier organization of the code, especially in a time crunch. The other thing too, again, if you use these motors, you'll notice that they don't often go the speed you think they will. They'll go slightly different. Each motor is a little bit different. And so when we put it down on the ground with the load, the robot ended up veering a little bit off to the right. And in a perfect world, we would use a PID loop, if you probably all know what that is. And what that allows is for the motor to go predictably, it allows it to correct itself. But we didn't have that, so we instead added a multiplier value to then tell the left motor go a little bit slower than the right. And so I want to talk about our prototype flaws for a second. So I would say the first flaw is that it's a little tricky. If you look at this robot, you'll see that the wheels are pretty close to the center. Now, this was a design choice for some reasons. For one, we could keep the robot pretty short, and 2, it ends up being pretty nimble and agile. But what it also means is the casters are back here, and right now it's fine. If there's a load here, it tends to tip over a little bit. We counteracted this with these nuts and bolts, which was actually a design choice because these are free. So we wanted to keep the cost low, which in the real world, we want this to be as inexpensive as possible. So that was why we did that. And another thing too, is we're controlling this with an IR remote. It's like controlling this with a TV remote. And in time-sensitive operation, that doesn't work very well. And so it relies on the remote being very close to the sensor and then being in a particular direction. If the robot's spinning in particular, you have to spin with it. In the real world, this would not be what you want to do. The remote would be useful for one reason though, calibrating the robot. As I go back here, there's a little photoresistor. And the photoresistor relies on certain thresholds to know whether the sheet is faulty or not. And in the real world, you will have different lightings, especially if you're selling these to clients. They might have one room that has different lighting schemes, and you need to be able to calibrate this. So if we were to go on and keep going, we would add the ability to calibrate this. And lastly, we would then probably add some autonomous mode. Because why would a company buy a robot like this is to probably save labor. And if there has to be someone operating the whole time, well, they're not saving much labor. And implementing autonomous mode would probably require computer vision. We wouldn't want to use a photoresistor because the light in real life would probably reflect a lot of light. So now to talk about our prototype strengths. For one, it's a pretty nimble little guy. It's small, and because the wheels are in the center, it can spin on a dime, which is in some ways really nice. If you were using this in real life, you would be able to sell it to companies that had small, compact factories with a lot of stuff in the way, which is often like a lot of factories available. And another thing is that this is a pretty mechanically robust design that's replicable. As was mentioned earlier, a lot of the things we did here, we envisioned as being analogs for things like sheet steel. And so that means that this robot is replicable and inexpensive, which then can be easily sold to manufacturers and industry. And so now I will pass it on to Ron, who will close up this presentation.
So here's our final build after 8 hours. In the end, we built what I believe is quite a robust design given the time frame. We definitely could have made some improvements by using an array of IR sensors to detect line changes, right? So we don't deviate off the line to provide automation features. We could have used steppers to make the movement more accurate, right? In an environment where DC motors are not as reliable. There was a lot of stuff we could have done, but honestly, I'm gonna quote the phrase that you don't know what you don't know. And given the time frame of a competition, you run into problems that you're gonna have to face, right? So you have to make adjustments on the fly. And I'm very proud of us all today for competing and honestly putting our heart out to bring to you what we believe is a great foundation that can be used in industry today. So here are some of the references that we utilized for our presentation. And finally, I'd like to acknowledge everyone here today for taking the time out of your busy schedules to support young aspiring professionals of the world today. And honestly, this has been Team Barnacle, and thank you all for listening.
Thank you.
Alright, judges, you've got 15 minutes to ask any questions.
Can you go back to that last picture you had on slide 26?
Sure.
So with the forks up like this, what's going on?
That is, so that's good one. This is actually in the middle position. Just when you turn the robot off, that's just what it goes to. It goes down and it goes pretty far up. And sorry, was it you who asked the question? Or-
Oh yeah, just
Yeah,
compare
hi,
it.
sorry. And then I just didn't. So then, yeah, the idea is it goes into the sheet and then it lifts it up.
Okay.
And then, yeah, carries off, and then where it needs to go, it then puts it down and then drives away.
It's important to keep in mind that this was designed specifically for the holder that we were presented with. We decided to be narrow with that focus because we had to solve the problem of sorting these panels as fast as we could and where they needed to go. Maybe in a real world you'd want actually some altitude adjustment with the forks, not just like a static pivot, because you might want them on different racks, different heights. Might be more of a forklift design. With the equipment we have, we couldn't really make elevation, pistons, anything like that. So this angle is highly specialized to the little holder, and that's why it's built this way.
Yeah.
We didn't want to overcomplicate it.
Also, one more thing. When we were lifting it, we had to account for the fact that if we lifted too fast, it might actually fall backwards. So what we did was we had enough cardboard indentation extruding out the top right here.
MDF.
So as we basically lifted it, then it would rest in a stable enough spot to drop it to its designated area.
Oh, sorry. Do you want me to move over there?
So you're relying on basically the friction with the forks to kind of hold it in place.
Yeah, we have a little indent too, so as it raises it up, the way it's placed is placed as an angle. So as you lift it at that angle, it's actually gonna slide this way because of obviously Newton's laws, right? There's a force going this way because of gravity, and then basically it's angular. So we already know the actual design problems, basically what's gonna happen. Like it's expected functionality as we lift it.
Let's touch briefly on thinking of the window, how it could potentially tip over and you guys countered that by adding some weight to the back. Have you since then tested it and seen that it functions well, that the center of gravity is kind of where it should be, and are you confident that it's going to be repeatable going forward?
There's actually like just a slight overcorrection because if we move slow enough, the moment isn't large and it doesn't tilt back. We want to just be extra safe and secure that it doesn't tip forward.
There is still a bit of tipping when
Yeah.
when it's loaded.
Yeah.
This would definitely be something we would have continued.
The higher the forks go, the further back that load will be, and will actually counteract that a little bit. But it's the additional lifting that generates that.
Yeah, the thing is with this specific design, we had to just commit. So if we drilled like a hole in the cardboard, we had to just go with it. Yeah, the MDF. We just had to go with it, and essentially as we built it out, we started testing in the end. So we had to, those screws are literally there just because it's like a last minute design decision.
Yeah,
Right?
we constrained
So,
ourselves to that
yeah.
one square 1 foot by 1 foot piece of MDF. We're like, let's try and build this robot out of just this because we were thinking it would be like analogous to sheet steel. So this is like a piece of sheet steel. Anytime you see hot glue, that's welding. And so we wanted to really transfer this to if a manufacturer wanted to take this prototype, build it in real life. We're not going to put any tape on this. We're not going to wrap anything in wire. We're not going to wrap anything in rope. That's not what you see in the real world. You see bolts, fasteners, welding. So anything you see that's made out of MDF, imagine it as sheet steel and maybe tube steel for the forks. And the bolts are bolts. So this really transfers well. But that was a challenge we had for ourselves. Was like one sheet of MDF. Yeah.
With hindsight, if you were to redo this competition, would you go with the same kind of small design, or would you go with
Probably extend it out a little further on the back end, just to counteract that
Yeah.
that tipping motion.
comments that how we have, like now that you made it very small to be able to turn on the dime, but then you have these long forks.
Yeah. It's really hard to adjust once you
Yeah.
start building it, just because it's like you gotta glue it, you gotta drill it,
But having
build,
the-
then test, and it's like you gotta go back and rebuild and re-glue, right? So it just takes time.
I mean, we could really still keep that high maneuverability and really short wheelbase and short body length. We just have to make it a little bit heavier. I mean, a stack of lithium ion, like lithium batteries, the best thing about it is that like some designs are really trying to escape the fact that they're heavy. This design would benefit from these really heavy batteries, long battery life. Yeah, so as well. So it actually, with the actual real batteries it would have, not just a 9-volt, this thing might be heavy enough to handle no problem with no tipping whatsoever.
To touch on your point, you can really see in these competitions how it's a very iterative process. Engineering in general is.
Yeah. So if you had like an extra hour with
That would help so much.
We didn't actually get a chance to go in and test on the
Yeah, that would be
test
nice.
area. Yeah.
How did you delegate tasks to do the programming, the electrical?
Yeah, so me and Jimmy did the programming, and these two handled the manufacturing for the mechanical design. And then what we did was we actually worked in GitHub, so we would just basically work on functions, and then we just integrated all together, so we could simultaneously work on the software as well together.
I love GitHub.
In the moment, kind of like Tom is a really strong coder actually. Tom and Jimmy in our last competition did all the coding, and Ferran and I did all the coding. I've kind of worked in trades all my life, so I have a lot of hands-on skill before I went to engineering school. So I'm really confident to build. But on the day of, Tom kind of just like he felt inspired, and he was just like, I think I could do this. I have a lot to lend to the mechanical stuff. And Ferran felt really inspired, and he was like, and we trust each other so much. So the delegation was like instantaneous. Just like Ferran and Jimmy were like, we got this, and Tom and I felt like confident, and there was like no friction whatsoever, which is weird. We vibe together pretty well.
And to touch on your point too, the task we tried to, when we could, work on like separate pieces, and then where I could, Ron and I could work on code, and then they work on a different piece where they work on mechanics, and switch off as much as we could. Sometimes it's hard though because like you can't. It's very different to test it independently than when it's in its whole system, and then problems arise there. Like for instance, one thing that we ran into was the IR receiver became a lot more unstable once the motors were running on it, because there's suddenly a lot of load and there's a lot of not crosstalk, but some.
Yeah, you have to look at the design like holistically.
Yeah, that's really important.
And that actually really reminds me of something that we didn't experience in the last competition that we weren't prepared for today, that we will improve if we ever did this again, was knowing the distance to travel physically, to walk all the way down to the basement to get to the workshop, and then being up in the room.
Having that divide,
Having that divide.
yeah, it really like cut us in half
Yeah.
as far as like integration with the firmware to the
In the last competition, we had all 8 of our hands on the robot, and some people were plugging in and programming, some people were like fastening all at the same time. This one, we had to like take the robot away from them while they were coding, go down and fix something, and then bring it back up, and they're like, hey, bring the robot. So it was
It's much easier to scope when everyone's around you.
We saw other teams do it better than us. They took their programmer and they took their builder, and they both took their little build clips, went into the workshop, and actually he put his laptop on the workbench, plugged it in next to them, and we really regretted not doing that. So
Yeah, next time what we probably would do is.
it was a great idea. We just it didn't occur to us. So it's good to recognize where like you can improve. That was a highly efficient move.
One thing I don't know if you touched on it, but you're just about how does the robot kind of tell people around it that it's in operation right now?
When the robot moves, there is this green light here, and whenever it's moving, the green light is on.
And the red light goes on.
When there's a
And we have a
And
buzzer.
or when
There's
there's a
a
pull.
buzzer.
It's also a buzzer. Yeah.
The buzzer indicates the fault window essentially.
And for, I guess when it's moving around, if you have workers in the same space, how are you going to let them know, like, if they're visually impaired, if they're hard of hearing?
Right. This would be. We have like lights and buzzers are the best we can do, but in the real world, I worked at a robotics facility last year, and one thing we did was it had sensors to tell when there were people around, which is. Are you familiar with cobots? whole thing with robots, because that's a really important point. Like there's a huge amount of time put into if there's someone around. If the arm is moving, there's sensors that can tell if there's objects nearby or people around, and it's really important that the robot slows down or stops. Usually, you actually want to slow it down a little bit and then stop, so you don't actually destroy the product you're working to. But yeah, we would definitely implement sensors that would be able to tell if there's people around when it's in operation.
In its current state, we have buzzers and lights. That's what we do with the equipment we had, but
Yeah.
totally, like real-time obstacle avoidance and collision avoidance would be the next step.
We try to build in the context of the competition for a prototype.
Yeah.
And try to just make it analogous to real life also.
Your design solution has 2 cancel wheels. Would you guys consider using the same cancel wheel?
Yes. Yeah, we've actually done it in a different robotics course. Tom has it too.
Yeah, and it especially if you're loading it and turning, there's lots of possibilities for tipping.
Yeah.
I guess in this case too, it helps to have a little more weight in the back. So
Yes.
Yeah, in this specific case, 100%.
Yeah, I was thinking that if you had the wheels far enough apart and then a third wheel at the back, you wouldn't have that tipping because the instability back, because these wheels are so far apart, it would be unlikely. But then we lose all that maneuverability. We were looking at the picture of the course, and it is a tight course. Like you can't have a really wide robot. And we actually think that compared to other designs that we saw, we think we have one of the most narrow robots, which we're proud of because that was a hard constraint to get within. So
Yeah,
we're
because
proud of
honestly,
that.
if we had more time, we could have probably all we would really have to do is kind of build like a layer system upon the center of gravity, right? So it would actually help with the placement of where the weight actually is. So when it does pick up the window, obviously you'd have to change it in real life, but in terms of this window, it's a cardboard, it's modeling the window. But yeah, we could have done it.
In real life, we would be using SolidWorks or something to do like do load calculations.
Yeah.